Hi, welcome to this recitation session on the method of images to determine electrical potential. So, initially we used Gauss's law as well as Coulomb's law to find the electrical potential in a point on space due to the certain charge configuration. And there is one thing that there are many instances where we cannot rely on these two laws, so that we have to rely on a different method to find the potential. So we are going to examine set one of the cases. So we have an infinitely spanned plane, and it is placed along the xy axis, so it will be parallel to this xy plane. So we put a positive charge plus q on this directly above this surface charge or this plane. This is a plane. We place a certain charge q at a distance d from this plane. Okay, and we have to find the potential at this green spot due to this charge. So if we are known that we can use Coulomb's law or we can use Gauss's law, we directly go and suddenly jump into this step and try to find potential using this formula. But this cannot be valid because there are some kinds of adjustments in the charge configuration that cannot be expressed in this equation. So let's check what happens. So this plane of sheet, this sheet is earthed, and the potential at this plane is considered to be 0. So if we place the plus q over at a distance d from this plane, the certain charge is formed due to induction. Okay, so this charge as well as this charge also contribute together to form potential at this point. So the two main charges are acting here, and of these two we are aware only about this charge, and we don't know what kind of charge or what kind of amount of charge is here. So we are going to find the charge induced in this plane sheet that can contribute, that has potential to contribute electrical potential on this green spot. So it's given that the potential at plane, the potential at z equal to 0, that is the potential at along the plane is deemed to be 0, so that we have to reduce this diagram into this diagram. See, so in this diagram we have the same plus q here, and we put minus q here, so that it creates a net potential of 0 here. So in order to satisfy the potential at the xy plane to be 0, we put minus q at the same distance d down from the xy plane. So this is the classic equation for potential, and we reach here. This is z minus d square. So this is very easy, as you are very much familiar with these terms. Hope you got what I had said so far. So we have said that in order to find the charge configuration, the induced charge due to the point charge, we have to consider many conditions, and the first one, as I have said earlier, is v is considered to be 0 at xy plane, and secondly, v tends to 0 at a far distance from the point charge. So these two conditions are the turning points that helps us to find the value of charge, induced charge on this surface or on this plane sheet. So we have the equation that we are very much familiar with, and this is the equation that we have drawn from this diagram. So we have minus q, and this is the minus q, and this 0 is as part of the condition that we have considered here. Okay, so it is that and that's the reason, this 0 is the reason why we consider minus q here, minus q over here. So the reduced charge configuration behaves like origin configuration, and this is the origin configuration that we have, and this is the reduced charge configuration we created for the sake of simplicity. So what it says that by placing minus q at the distance d, by placing this minus q at a distance d below this charge configuration, below this plane sheet, we can treat the problem that we have encountered. So this considering of minus q, or this minus q that we have taken, is called the electrical image of plus q. So we have used the electrical image or minus q to encounter this problem. So we can say that the minus q behaves as an electrical image of plus q. So the question arises, what is electrical image? An electrical image is a point charge that is a point charge on the one side of plane. So this is a plane that we consider here, and it's a point charge which occupies at one side of this plane, and this point charge creates the same electrical field as that of the electrical field produced by this plane sheet. So we have the plane sheet sigma, and we have the charge, consider plus q in this case. So this two charge configuration produces the same electrical field. So we can say that E due to this sigma, this surface charge or this plane sheet, is exactly the same as this. So the plus q, this charge acts as a substitute for the plane sheet or the plane sheet charge configuration. So this is the electrical image. So you can read and you can pause and think. As we have said earlier that the potential at this plane sheet, at this xy plane, is 0. So we can assume that the potential only happens to be at a distance, at an altitude where z is greater than 0. So that's the reason why we put this sign. So we can fill the blank here. This is normal geometry, 3D geometry we use here. This is for the plus q charge, and this is, you can fill it by yourself. Or the minus q that we considered, and this minus q is the what is something called electrical image of this. So by knowing boundary condition, we can find V and E. So by this boundary condition, the boundary condition is such that V is 0 at, or we can say V of xy, V over the plane is 0, and V goes to 0 for a distance very distance greater than d. So this is the two boundary condition that we have, and based on this boundary condition we can find V, and from V we can find electrical field by del V minus del V, and from this E we can find the charge. So let's enter the summary of the drama. So we have to find, we all know the relation between the electric field and as well as the potential. So the electric field is E equal to minus dou V by dou N, where N is a distance that we have taken, and along this N or along this N cap we feel electrical field. So in this case we would like to focus on magnitude. So this is the magnitude, not magnitude, we neglected the direction. Okay, so this is the expression for finding electric field due to the potential. The electric field is the negative gradient of potential. And also we know that for the infinite charge plane configuration, suppose we have charge, for the sake of simplicity we take plus charge, positive charge, and electric field at any distance due to this charge configuration is sigma by epsilon, and that goes perpendicular to this direction. Okay, the same thing happens here. What we do now onwards is we just try to equate them, and this is what happens. And we took this epsilon over here, and since we put the charge, the plus q charge over the plane sheet at a distance d along the x-axis, that means our charge lies on the, sorry, I withdraw my statement. Since we placed the positive charge at a distance d above the xy plane, above the plane sheet, we can consider this n as z, because we placed the plus q charge along the z-axis. And now our job is to find the value of sigma out of from this potential. So we take the derivative with respect to z, and what we get is this one. You have to check and verify whether you get this, and you can take this differentiation as a kind of exercise. So what we end up is the sigma is equal to this, we have epsilon here and we have epsilon here, and that gets killed off. So we have qd. So we have qd, and how 2 pi and xy square. This is what we have. Okay, so you might have noticed there is some silly mistake. You have to consider this negative, because this negative is very important. That helps us to arrive at conclusion that the induced charge, and this is the induced charge density, hence the induced charge is negative, and its maximum at x equal to y equal to 0. So the induced charge is, as you can verify, this gets maximum value when the denominator gets reduced. So we have to find the total charge. So what we have got is sigma. In order to find the total charge, we have to integrate over the area. So we perform surface integral. So we have r equal to root of x square plus y square. So for the sake of easiness of double integral, we use polar coordinates, and this is the elemental area in polar coordinates, and this is we have x plus y square, and it's substituted by this, and we do here, and this is the step. Okay, we can observe from this step, and we get minus q, so that the charge induced, or the charge that we had to find, or the induced charge, is minus q. Okay, now we have to find the force and energy to set up this charge configuration. So initially we put plus q, and as a result of inducing of charge, and we found that minus q is the induced charge, and there is a Coulombic force acts between them, and the distance between them is d plus d the whole square, and this d plus d is formed due to this d plus d is originated from the diagram, from the reduced diagram. This is the diagram. Here we have d, here we have another d, and this d plus this d and this d together contribute plus 2d. So this is the force that happens when this kinds of charge setup occurs. In order to form this system of charge configuration, where we have plane sheet and the plus q we place over directly at an altitude d, we have to perform work. Without performing work, we cannot put this into stable form. So we would like to find out the work that we have to do, and here we have, this is the Coulombic force. We have to act a force against this force, so we use plus F against the Coulombic force, and since we put the charge along the z axis, we would like to use z, and the z is along x cap, and the force acts along the x cap. Remember, the force is experienced along the x cap, and we put, so consider this as a plane, and we try to bring the charge over here like this. So what happens is, it turns out to be that we displace charge along the z axis. So we have to consider the z coordinate, this z unit vector k cap, and we perform the normal integration procedures, and what we end up is here. Okay, you can observe this derivation. It's very simple, pretty easy. So what we have learned, that we have used a different method, we have used a different kind of treatment to find the potential in one among the various charge configurations. Thank you.